The rational root theorem. The rational root theorem is a way to try to find the rational roots, that is the zeros of a polynomial of the form m over n, where m and n are both integers and n does not equal 0. That's what a rational number is. Basically a fraction. That's the way a lot of people think of it. But a fraction of only integers. So the rational root theorem does not tell you the roots or the zeros of a polynomial. It says if there are rational roots, it must be found in one of these. But one of what? Well, the possible rational roots of a polynomial are all the possible factors of the constant term divided in turn by all the possible factors of the leading coefficient. If that doesn't make sense, let's do a couple examples to see if it helps you understand it. So suppose I have the polynomial, let's say x to the fourth plus 3x squared plus 10x plus, let's say, 4. This back here is my constant term. The number in front of the highest power, in this case, has implied that it's a 1. That's my leading coefficient. So what are the factors of the constant term? Well, it's 1, 2, and 4, but it could be either positive or negative. Those are the factors of the constant term. What are the factors of the leading coefficient? Well, it's only 1. If the leading coefficient is 1, then the factors are only 1. Now, I don't need to do plus or minus. I already counted for it. So technically, I should divide all of these by 1, which means the possible rational roots are plus or minus 1, plus or minus 2, or plus or minus 4. If there are any rational solutions to this equation, f of x equals 0, it will be found in here. It doesn't mean one of these work. It doesn't mean any of these work. If none of those work, it just means our solutions are either irrational, generally speaking, have square roots in them, or imaginary, have i's in them. Let's do another example, slightly more complicated. What if I have g of x equals, let's say, 2x cubed plus 7x squared minus 10x, and then we'll do plus 6. The 6 is my constant term. The factors of the constant term are 1, 2, 3, and 6. Don't forget plus or minus. The factors of the leading coefficient where my leading coefficient, the coefficient with the highest power, is 2. So the factors of the leading coefficient are 1 and 2. I don't need to do plus or minus. We already counted for those. So how do I get the possible rational roots of g of x? Well, I have to do all of these in turn divided by all of these, meaning plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. But also all of those over 2. Plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 6 over 2. So all of these divided by all of these individually or in turn. So it's all of these are the possible rational roots. But then I go back and look to see if I have any repeats. I see that 2 over 2 is 1, so I don't need to repeat that one. 6 over 2 is 3, which I already have up top. So what's left over are the possible rational roots. How can we do this? That is, how can we use this in a problem? Well, let's consider the function f of x equals x cubed minus 3x squared minus 10x plus 24. And I want to find the zeros. Not the possible zeros. I want to find the zeros of this function. Now I am going to start by listing the possible rational zeros. So my constant term is 24. My leading coefficient is 1. The leading coefficient of 1 makes this a little bit easier. So the possible rational roots will be one of these. It'd be the factors plus or minus of 24. So plus or minus 1, or 2, or 3, or 4, or 6, 8, 12, and 24. If I left any off, make sure you add them in. So there are 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 possible rational roots. Which one of these, if any, gives us a 0? You might say, man, that's a lot of work. Yeah, I agree. But since there are an infinite number of integers and an infinite number of rational numbers, at least this gives us a starting point. So let's check. Is x equals 1 a solution? Let's do synthetic division. I'll put the 1 right there. And then I'll put my coefficients of my polynomial, making sure I have a coefficient for every power, including ones that are left off. Let's do synthetic. We'll put the 1 there, and then we multiply, place, add, multiply, place, add, multiply, place, and add. Is my remainder 0? No. So x equals 1 is not a solution. Let's try x equals 2. We'll do the same thing, but put the 2 up in the box. Place our coefficients down. If you're not following along with synthetic division, just go back and watch the video that I put out on this. Then we'll put the 1 down, then 2 times 1, place it there, add, multiply, place, add, multiply, place, add. We get a remainder of 0. So x equals 2 is a solution. Not only that, I know that it's a factor, and what's left over is x squared minus x minus 12. What we really like to do is get whatever polynomial we have down to a quadratic so that we can either factor it or use quadratic formula. And let's see if this one will factor. It looks like it will. Which means I don't need to check anymore. I have all of my solutions. X equals 2, 4, and negative 3. Let's try one more. What if we have f of x equals 2x to the 4th minus 9x cubed minus 12x squared plus 29x plus 30. Oof. What are the possible rational zeros or possible rational roots? Well, it's all the factors of 30 in term plus or minus divided by all the factors of 2. So plus or minus 1, 2, 3, 5, 6, 10, 15, and 30 divided by both 1 and 2. So I'm not going to finish that off just because there's a lot there. And, of course, I already know the answer. But let's try a couple. Let's pretend that I don't. It could be plus minus 1 or plus minus a half, right? It could be plus or minus 2 or plus minus 2 over 2. I already have that. It could be plus or minus 3 or plus minus 3 halves. All right, let's just try x equals 1. Does x equals 1 work? We'll do synthetic division. Putting my solution in the box, x equals 1. The coefficients of my polynomial don't have any missing powers, so I don't need any extra zeros. And synthetic. 2. Multiply, place, add. Multiply, place, add. Multiply, place, add. Multiply, place, add. Does not equal 0. Not a solution. Let's try x equals negative 1. Same idea with synthetic. Put my solution in the box, my coefficients, and then bring the 2 down, then multiply, negative 1 times 2. Place it, add. Multiply, place it, add. Multiply, place it, add. Multiply, place it, and add. And I see that x equals negative 1 is indeed a solution, which means that x plus 1 is a factor. Let's try the next one. What about x equals 2? Watch what we do here. I could go back and use my original polynomial, but why? I already have it simplified. I already know that x plus 1 is a factor, which is going to leave me 2x cubed, right? Minus 11x squared minus x plus 30. Whoops, let's put a 1 there instead of an x. So we can do this, the synthetic, on what's left over instead of the original one. It's just going to save us time. So let's bring that down, and then a reminder, in case you didn't see the synthetic video, we do 2 times 2, which is 4. We place it right there, and then we add those. Then 2 times negative 7, place it right there, and then we add. Then 2 times negative 15, place it right there, and add. And I found another solution, which means I found another factor. So now that I'm down to a quadratic, and how do I know it's a quadratic? Well, I went from 4th power down to 3rd power down to quadratic. I have the following. My polynomial is x plus 1, I know that's a factor, times x minus 2, no, that's a factor, times what? Well, let's interpret this here. That's 2x squared minus 7x minus 15. If this factors, great. If it doesn't factor, we use quadratic formula, but either way, I don't want to do any more synthetic or even long division. So let's see if this will indeed factor. 2x and x right there. I think if I put a -5 and a +3, I see that it does factor. So not only do I have my original polynomial in factored form, I have all my solutions. X equals -1, +2, -3/2, and +5.